In this lesson, we're going to continue to look at electromagnetic induction. This time we're going to look at the electromagnetic induction in a loop, or coil or solenoid. So remember from the last lesson, we learned that you can induce an electrical potential difference in a single conducting cable like this, just by moving it through a magnetic field. Okay, so we learned that as we move the cable through the magnetic field, what happens is, due to the motor effect, electrons in the cable are pushed towards one end. Okay, so you get a build-up of negative charge around this end of the cable, and therefore a positive charge is left at this end, and that causes an electrical potential difference or voltage across that cable. Now, if you want to look at the details of this, then I suggest you go back to the previous lesson and have a look at that. But what we learnt was that this isn't particularly useful at the moment, because although we've generated a voltage or an EPD, we haven't produced a current, and what we need is a current. And in order to have a current, then you have to have a closed circuit. So instead of using a single cable like this, we're going to adapt that to form a loop. Okay, and when we do that now, the electrical potential difference which is produced in this section will now drive a current around that loop. Okay, this build up of negative charge here will force the electrons to move in this direction. Okay, that's going to be the direction of the electron flow. Okay, so they're going to be pushed around the circuit in that way, but remember that the conventional current direction in electricity is always opposite to the electron flow. So by convention, the current will flow from positive to negative. So that becomes the directional current flow. So we'll write that there, that's the flow of the current. So pushing this loop into the magnetic field this way will cause a current to flow in an anti-clockwise direction, in this case from positive through to negative. Okay, so that's what happens when we push the loop into the field this way. Okay, if we reverse the direction of the loop, then the electrical potential difference across this section of the loop will change sign. The negative charge will be pushed this way, and the positive charge to this end. So we get a negative at this end, positive this end. We change the sign of the voltage, the EPD, and so as a result the electron flow will change direction and the conventional current direction will change. And if we were to insert an ammeter into the loop, okay, like that, then we will see that the needle of the ammeter would flick backwards and forwards from positive to negative as we move this loop into and out of the magnetic field. So we get what we call an alternating current in this loop. The current would be continually changing as we move the loop in and out of the magnetic field. Now, as it stands at the moment, this single conducting loop doesn't produce a very large electrical potential difference, and therefore the current flowing in the loop won't be that big. So if we want to increase the electrical potential difference generated and consequently the current, then what we can do is we can increase the number of loops. In other words, we can wind this cable into what is called a coil or a solenoid. Okay, so instead of the loop we've got this. Okay, so we call this a coil or a solenoid. It's not a circular solenoid, it's a rectangular solenoid, but it's still a solenoid. I've done it in a rectangular way just to keep things simple. So what we're going to do is we're going to move this solenoid in through the magnetic field this way, and this section of the solenoid here is going to cut through that magnetic field, and as before, what's going to happen is that an electrical potential difference is going to be produced in each one of these sections of the loop. So what you get is you get an electrical potential difference or voltage produced in this part, and then in this section, and then you get another electrical potential difference of equal size produced in this section, and then in this section, and in this section. So what's happening then, in each section of the loop you're getting an EPD produced or a voltage produced, and so what will happen is the voltage produced in each of these sections will add up in series. So it's as if you've got a whole load of little voltaic cells which are connected in series here. representing each section here of the loops in the coil, and these will add up and result in a much larger electrical potential difference generated, and therefore a greater induced electrical current. Okay, so what does the size of this generated electrical potential difference or voltage depend upon? Well, as we saw in the previous lesson, first of all it depends upon the speed of the conductor cutting through the magnetic field. So greater speed results in a larger current. Secondly, it depends on the strength of the magnetic field. So we can say a stronger field produces a larger current. And thirdly, as we've just seen in this section, we can greatly increase the size of the voltage induced in our conductor by changing the conductor into a solenoid. That's to say, increasing the number of loops in the solenoid will result in a greater generated electrical potential difference or voltage. So we can say more turns, the greater the number of turns or loops in the solenoid, the greater the current generated. Okay, so in the next lesson what we're going to do is we're going to have a look at a practical adaptation of this setup to produce a useful AC generator.